Hello everyone, respected faculty. I am Kammari Vishnu Teja. Today I am giving a seminar about seminar or presentation on uncertain graph sparsification. I am from CSC H section, subject mathematics for computing. Introduction of this uncertain graph sparsification is uncertain graphs are graphs where edges have associated probabilities representing their existence. Uncertain graph is where a graph where edges aren't guaranteed. Each edge has a probability of existing, where they are used in systems with uncertainty like social networks or biological networks. They are used to model systems with inherent uncertainty such as social networks and biological networks. Understanding and managing these graphs is crucial for efficient analysis and computation. Graph sparsification means making a graph lighter. By lighter means by reducing edges but keeping importance properties. In uncertain graphs, the big challenge is to remove edges while still keeping the probabilistic structure intact. Next, what is graph sparsification? Just now I have said where classical two valued predicate logic assigns true or false values to formulas. It provides a foundation for formal reasoning and logical inference. The logic simplicity makes it fundamental tool in mathematical logic and computer science. Sparsification means makes a graph lighter. The need of it is large uncertain graphs are hard to analyze, so we sparsificate those graphs. And it is a very big challenge to remove edges while still keeping the probabilistic structure intact. Means next, it is a big challenge to sparsificate uncertain graphs. The topic is challenge of sparsification in uncertain graphs. Uncertain graphs add complexity due to the probabilistic nature of edges. Due to its complexity, the nature of edges, preserving probabilistic properties during sparsification is a major challenge because when we don't preserve the probabilistic properties, the graph may misbehave or the information will be wrong. Traditional sparsification techniques often do not directly apply to uncertain graphs. Motivation for uncertain graph sparsification. Motivations means large uncertain graphs demand efficient algorithms for analysis and visualization. Sparsification helps in reducing storage and computation costs because sparsification makes the uncertain graphs better. So it reduces the storage cost because we don't buy or extend our storage by buying it, and it reduces computation costs also. Accurate sparsification ensures the reliability of downstream tasks like routing, clustering, and prediction. Sparsification also do maintain probabilistic connectivity between the graphs which are uncertain, and it preserves the key structures like shortest paths and cuts. And also It balances between fewer edges, that is sparsity, and accuracy between them. Key objectives of uncertain graph sparsification: maintain the it maintains graph sparsification maintains the probabilistic connectivity between nodes, preserve important structural properties such as shortest paths and cuts, achieve a balance between sparsity and approximation accuracy. Means it maintains connectivity between nodes, preserves important structural properties such as shortest paths and cuts, achieve a balance between sparsity and approximate accuracy. Without that, the sparsification can't be completed. Measures of approximation quality: probabilistic cut preservation measure how well cuts are maintained after sparsification. Approximate preservation of connectivity probabilities ensure the graph integrity. Metrics like spectral similarity can also be used to evaluate sparsification quality. Spectral similarity can be used to evaluate sparsification quality. Quality can be measured by metrics like spectral similarities and probabilistic cut preservation means the cuts remain similar, so it is checked as quality. Connectivity probability stay close to original. Spectral similarity, I have said it. The main approaches to uncertain graph sparsification. Sampling based methods that select a subset of edges based on probability thresholds. Optimization techniques aim to minimize the difference between original and sparse graphs. Hybrid methods combine probabilistic sampling with structural heuristics. Sampling based methods are they keep edges based on their probabilistic or importance. They always keep the edges in the mind of in the on their probabilities or importance, and also more reliable edges are kept more often. Optimization based methods all they formulate as a math problem, minimize error between original and sparse graph, uses convex or combinational optimization but costly. Sampling methods based methods are cheaper than optimized based methods. Hybrid methods usually they are combined between sampling and heuristics, but mostly sampling based methods are used because optimization techniques are but a little costly. Next, sampling techniques in detail. Sampling techniques: edges are sampled with probabilities proportional to their original importance probabilities or importance. This method ensures that more reliable edges are retained with higher likelihood. Careful sampling preserves key probabilistic properties of original graph. In uncertain graph, sampling techniques play a major role because this method ensures that reliable more reliable edges are retained with higher likelihood, and they preserve key probabilistic properties of the original graph. Next, the optimization based methods. Optimization based method formulates sparsification as an optimization problem to minimize approximation error. They use convex or combinator, combinatorial optimization techniques to find near optimal sparse graphs. These methods often involve complex algorithms with higher computational costs, and also uses convex or combinational optimization, but they are costly. Since I have said they formulate as a math problem, minimize errors between original and sparse graph. They use convex or combinational optimization techniques to find optimal sparse graphs. Spectral sparsification in uncertain graphs. Spectral methods aim to preserve the Eigen values and Eigen vectors of the graph Laplacian. They ensure that the graph's global structure remains similar post sparsification. These spectral sparsification ensure that graph's global structure remains similar after the sparsification also. Spectral sparsifiers are particularly useful for tasks like clustering and semi-supervised learning. Spectral sparsifiers are particularly used for tasks like clustering and semi-supervised learning. Usually, spectral sparsifications are used for special cases. They preserve Eigen values and Eigen vectors of the graph Laplacian. They are useful for clustering and semi-supervised learning. Theoretical guarantees. Many sparsification algorithms come with probabilistic error bounds. Guarantees ensure that key properties are preserved within specified tolerances. Such theoretical insights provide confidence in sparsification progress. These theoretical guarantees provide sparsification process the confidence of uncertainty, removing the uncertain graphs. Many methods come with probabilistic error bounds, gives confidence that important properties are lost. Applications of uncertain graph sparsification. Social network analysis between from sorry, I'm so sorry. Social network analysis benefits from simplified yet accurate models. Biological networks use sparsification for efficient pathway analysis. Infrastructure networks use utilize sparsified graphs for robust routing and planning. Social networks simpler but accurate analysis. Biological networks are efficient pathway study. Infrastructure networks are used for robust planning and routing. That means social networks are used for simplified yet accurate models. Challenges and litigations. Balancing sparsity and accuracy remains difficult, especially for highly uncertain graphs. Computational complexity can be high for large scale graphs. Ensuring the preservation of multiple properties simultaneously is very challenging. These are the challenges. Balancing sparsity and accuracy. Balancing sparsity, especially for highly uncertain graphs, is a very big challenge. Complexity can be high for large scale graphs and it may cost. Ensuring preservation of multiple properties simultaneously is also challenging. Key points for future search. Exploring dynamic graphs, uncertain graphs where edge probabilities change over time. Improving approximation guarantees with the more efficient algorithms. Extending sparsification techniques to hypergraphs and multi-layer networks. So, exploring dynamic and uncertain graphs where edge probabilities change over time. Improving approximation guarantees with more efficient algorithms. Extending sparsification techniques to hypergraphs and multi-layer networks. Summary. Summary of this Uncertain graph sparsification is development of scalable algorithms for large uncertain graphs. Use of machine learning techniques to guide sparsification. Integration of domain knowledge to improve quality of sparsification. We have seen integration of domain knowledge to improve the quality of sparsification. Use of machine learning techniques to guide sparsification. Thank you for listening my presentation. Thank you, ma'am.